Okay, good morning, class. Again, we are back here in session 4 for our lab. We're doing our 4th lab where we're going to discuss series and parallel circuits. Now, just to reiterate, the skills that we have discussed in the experiment so far, these skills, we hope that they continue to accumulate and that you use these skills to complete the rest of the lab assignments that you have to do. Now, what skills am I talking about? These skills you should have already learned based on the stuff that we covered in the class and also in the lab. So what are those? How to use the breadboard. So you need to know, okay, this is the breadboard. How do I use it? How do I use it to connect things, right? So you need to have learned how to use the breadboard. Secondly, you should have learned by now how to use the digital multimeter to measure resistance, to measure voltage, and to measure current, because that's what we do for the rest of the lab. We use the meter to measure resistance, to measure voltage, to measure current. Now, of course, we study the principles involved so we understand what current is, what voltage is, what resistance is. And also with the different circuit configurations for series and parallel, we also study to understand what we should expect from these different circuits. The next skill that you should have already, that you also should have learned is, or that we need going forward, how to connect the circuit from a schematic diagram. So if you have a circuit diagram where you have the different symbols, you need to know, okay, how do I connect this circuit? So it's so again, that skill is taking a circuit diagram and taking the components and creating that circuit on the breadboard. That's very important for you to know. Number 3, we have recording the data. So as you make your measurements, you need to record that data. And step number 4, very important, is to complete the lab report. You need to take that data and write the lab report, and then you need to be able to present your work, right? Be able to share what the report is saying, right? So today we're going to go through this very briefly. The lab today involves analysis, simulation, and also measurement. And so you need all 3 of these sets of data to complete the lab report. So again, I'll share my screen and go to the course. I'm going to split up this. I'm going to split up the handout into 2 pieces because I realize that it may be confusing or it may be overwhelming to some persons. So in the first part of the lab handout, we're going to have just the theory. So we have the objectives for the lab, and we also have the theory as well. Now the theory essentially gives you information about Ohm's law, information about series circuits so that you can identify them. Also information about how you get the resistance in series circuits, how you calculate the power in series circuits, how you also calculate the what is Kirchhoff voltage law, and all the equations that you need to solve a series circuit are presented there. Following this, the first part will also give you information on parallel circuits. So you can identify a parallel circuit. You can calculate the resistance in a parallel circuit. You can also understand Kirchhoff's current law, and all the equations for a parallel circuit are also presented. There is also some information presented on simulation, what is simulation, and so forth. So this is in the first part of the lab handout. In the second part, we just have instructions, and the instructions tell you what you need to do. So let me share the second part of the lab report. So this is part 2. And if you notice, part 2 only will have the procedure. So the first thing we have in part 2 is we have the circuits that you are going to build. We're going to use a 100 ohm resistor, a 220 ohm resistor, and a 1 kilo ohm resistor to create a series circuit and also to create a parallel circuit as well. The second picture here shows what your circuit is going to look like when you build it using Multisim Live. Okay, so again, if you look at the procedure here, it tells us that we need to be able to identify the resistors. So these resistors that we're going to use, you need to know which is which. And so there are 2 ways you can do that. You can look at the resistor color code of the resistors that you have, and you can find out, okay, which is the 100, which is the 220, and which is the 1K. Some of your resistors are labeled in the package so that you can use that to identify the resistors as well. Okay, so this is the first step to identify the resistors. The second step is to actually measure the resistance of those resistors and put it in the table provided. So if you notice here at the bottom of your page, there is a data sheet. And the first section in the data sheet is so that you can put in the resistance of your resistors, R1, R2, and R3. And the second step is to record your measured resistance. And so I will show you in a bit how we measure the resistance as well. We'll go through it very quickly. So the first part talks about the series circuit. And here it asks you to do analysis for the series circuit. What is analysis? This is where you use all the equations that govern the circuit to calculate the unknown values. Now, I did give you a resource for that. That resource, I'm going to highlight it. So again, here it opens with a parallel circuit. So again, you can see a graphic where you're measuring the equivalent parallel resistance. It gives you some facts about the parallel circuit, followed by some equations that you're going to use to govern a parallel circuit to calculate your unknowns. And then we have an example, a live example, where the problem-solving method is used to obtain the results. So you need to do this for the given circuit, right? Secondly, there's a slide giving you some facts about series circuit and also the equations that you would use to describe a series circuit. And then you have an example with 3 resistors. So this is complete. You're going to just substitute in the resistors that you have for the lab, and you're going to use this problem-solving method to obtain the unknowns, right? So what unknowns are you going to obtain? You need to obtain the unknowns that are presented in the procedure. So the procedure asks you to find a number of values. You need to find these and put them in the table. Likewise, and you're going to repeat the same thing for both series and parallel, and you're going to put your results in the table. So what is that? If you go down to the bottom of the page here, we have a table here. Whatever results you get for your analysis for the series circuit, you're going to put them up here. Whatever results you get for the parallel circuit, you're going to put your analysis results here. After you have done the calculations and you obtain those results, you put them in your table. Then you need to move on to the simulation. And so in the simulation, we are going to use Multisim Live, and you are going to go ahead and simulate your circuit. Your circuit should look just like this right here. So now I'm going to go over to Multisim Live, and we are going to build our series circuit and our parallel circuit. So go to the website here. So on here, we have an entitled circuit. I'm going to change the name. So the first thing you want to do in your simulation is you want to go ahead and grab your symbol. So I'll grab the symbol of a resistor, and we're going to put it on the page. And I'm going to come back and get another resistor. So the series circuit has 3 resistors. So I'm going to just grab 3 resistors here, and I'm going to build the circuit first. So the first step is to get the components. If you're going to do the simulation, first step is to get the components. So I just got 3 resistors and I got the ground. Now I'm going to go on the sources and I'm going to grab a DC voltage. And after you have gotten all your components, which is step 1, then you are going to connect the components to form a circuit. Again, the definition for a circuit is a closed path for current to flow. So you must have a closed path to have a circuit. So this is going to be my step 2. So I just built the series circuit, and the next step, I need to go ahead and change the value. So the value of this one is going to be, and so on the right hand side, you can see the value. The value of this one is going to be 100 ohms. So I enter 100. I'm going to change the value of the second one to 220. And now, so again, step 1, to get the components, put them on the screen. Step 2, to connect them together in a circuit. Step 3 is to change the values to the appropriate values. Again, we should have 5 volts here. Step 4, we are going to now include the measuring, the points for measurement, right? So we need to measure voltage. Now again here, you are told to measure the voltage across the components. Now there is no instrument to measure the voltage across the components. So what you're going to do, you're going to measure the voltage before it and after it, and then you are going to subtract these two voltages to find the voltage across it. So what do I mean? We know that the voltage here is going to be 5 volts, correct? So we are going to then measure the voltage after the component to see, okay, how much did the voltage decrease by? Whatever the voltage decreased by is the voltage drop across that 100 ohm resistor. Okay, so, and I'm just going to space out my components so that I'm going to space them out a bit so that when they are measuring, everything is going to be legible. So again, let's measure voltage again, and we will measure the voltage. So again, we're going to measure the voltage before the component and after the component. And this is how we can tell the voltage difference across the component. And you will see what that looks like. And so for the last one, I'm going to use voltage and current, so at least we can know, okay, what is the current that is flowing in the circuit. All right, so this is the series circuit. We can go ahead and get the simulation results. But what I'm going to do, I'm going to go ahead and build a parallel circuit as well. So to do that, let me get some more resistors. Oh, in fact, I can just copy this. Let me see if I can hit Control C. Okay, can I copy and paste? Okay, it says duplicate. Okay, so I'll duplicate this resistor. I need to rotate it. Let me rotate it. I'm going to go on this one and duplicate it as well. And put it down and then rotate it. I'm going to go to this resistor and duplicate it as well. And bring it down here and rotate it. So now I'm building the parallel circuit. So I'll also do the same for this power supply, just duplicate it. And also the ground as well. So this is step one, just to get the components. Then I need to connect the components. So this is going to be step two. So again, in connecting the parallel circuit, we know that all the components are connected. They have the same potential across them. And we also know that the current that is flowing in the circuit is based on the resistance of the resistor. And again, Ohm's law tells us that the larger the resistance, the smaller the current. The smaller the smaller the resistance, the larger the current. So for this circuit, we need to measure the current in each branch. So I'll go here on the instrument here and get the current. And we're going to measure the current flowing for each resistor. Okay, when we run the simulation, all the results are going to appear on the screen. And of course, you can definitely copy that so you can put it in your lab report. So just to help you, I'm going to start a lab report and show you what I'm going to put inside of it. We'll also measure the total current. That's the current coming from the battery. And maybe I'll measure the voltage and current so you can see what the voltage from the battery is. Okay, let me try to move everything and see if I'm able to select it, because they look like they're too close together. All right, let's see if we can move the top one. I think we can move them. So I'm just going to move everything up a bit. Okay, let's move this guy here. And move this guy here. And this one, we can move it there as well. Now, keep in mind that we are measuring the current in each branch, but we said that this is going to be equal to the total amount of current. So like if you look at here, the total current goes here and some goes there, some goes there, and the rest goes there. So if we measure the current here is going to be equal to the current for this branch and this branch. So let's go ahead and measure it just so we can know what it is. All right, let me move this around just so that we just so that we can have some separation. All right, I think we're good to go. So again, the circuit is built. We selected the components, then we went ahead and we selected the components, then we went ahead and we connected the circuit, then we went ahead and we changed the values so that the values reflect the correct values that we want. Then we added our measurement instructions. The last step is going to be to run the simulation. So we hit play here, and you can see that all the values from the instruments are being measured on our screen. Now I see we have a negative current here. That is because notice the arrow is going down. So I'm going to just change the arrow because it's measuring the current going into the battery. I'm going to change it so that the current is actually going to be the current coming from the battery. So now it looks like the current is coming from the battery. When I run the simulation here, now you can see I have all the results. I have the voltage at this point. Now, this is what I was talking about. How do you find the voltage across this 100 ohm resistor? You measure the voltage across it. So you subtract the voltage before it from the voltage after it. So that voltage is going to be 5 minus 4.62. And we can find the voltage across R1. How do you find the voltage across R2? It's going to be 4.62 minus 3.78. And you get the voltage across R2, correct? And then the voltage across R3 is whatever this voltage is here, because as you notice, after R3, the voltage is 0. So it's going to be 3.78 minus 0. So the voltage across this is 3.78. Again, Kirchhoff voltage law tells us for a series circuit, the resistance with the resistor with the highest resistance will have the highest voltage drop across it. That's what it says. Okay, the resistance with the highest voltage drop is going to have the highest voltage across it. So this 1K has 3.78 volts across it. Whereas this 100 ohms, when you subtract these two, you will see that it has about 0.37 volts across it. Let's look at the parallel circuit. Again, how do you get your results for the parallel circuit? We can get the total current here, correct? We know the voltage is 5 volts. The current for I1 is going to be 50 milliamps. The current for I2, 22 milliamps. The current for I3, 5 milliamps. Now you can also see that the smallest resistance has the most current, and that's what Ohm's law says. Ohm's law says that V is equal to I times R. So if your R is small, so again, if you say that I is equal to V over R, if R is large, you're going to have a small I, so small current. If your R is small, so V over R, your R is smaller, you're going to have a larger current, right? So so you can see that the total current, 77, is going to be 50 plus 22 plus 5. Okay, we also measured the current here. We said what happens according to Kirchhoff's current law, that the currents add up. The current coming in is equal to the current going out. So notice here, what is the current at this point is going to be the current of this branch plus the current of that branch, right? So you can see that's 5 plus 22, which is 27. So you need to take a picture of this for your lab report. So I'm going to do a sample lab report just so you can see going forward, right? So to do that, I'm going to open up a Word document. So just to give you a tip on how you will move forward with your lab report. So I'm going to say this is figure 2, and I'll put here simulation results. for series and parallel. All right. So this is simulation results. So what is the results? I'm going to copy this picture right here for my results. So I'm going to use the snipping tool. So if you don't know the snipping tool, just type SNIPP. You can see it here. And then I'm going to say new. And I'm going to snip the portion that I want to save. So this is it. And then I go back to the snipping tool and I hit copy. And I go back to my Word document. And I'm going to paste my picture right there. So now I have my results already for my simulation. So I can look at this picture and then I can put the data in my table, correct? Okay. Secondly, so this is this results. The next thing you want to do, you want to enter these results in your table. So let's go and get the table. So if I go in part 2, I have the table right here. So I can start putting that data inside of my table. Let's go ahead and copy this lab sheet. And I go to my my document. Okay, so for the series, I can put my information in the table. What is the total current? I can see the total current from the simulation. On here is going to be 3.787 milliamps. So I can put it right there. I can go back and calculate, okay, what is VR1? Of course, it's going to be 5 minus 4.6. It's going to be 0.37 something. So I'll put it right there in the table. So again, you go back and forth with your picture and you put your information in the table. For example, what's IT for parallel? IT 77.72 milliamps. So I go for parallel. What is IT? 77.47 milliamps. So again, you put your data in the table from the picture. Some things you do not have in your simulation results, so you don't need to include them, or you can decide to calculate them as well. Okay. Now, lastly, I asked you to measure voltage from 2 to 3. So the voltage across 2 resistors, in this case, is going to be the voltage between this point and 0. So that voltage will be 4.621. And I can put that for VR to 3, 4.621. So this is the simulation results for the series circuit. Okay, you will do the same thing for the parallel circuit as well. Okay, so what is the next, what are the other instructions after we have completed the simulation? So I go back up here on my page here. I can just go ahead and save this. So I'll stop the simulation and I'll make sure that this is saved. Save. And I can just put the tag, just say series parallel circuit. Okay, so this is saved already. So we're gonna move on to the next step. So if we look at our procedure for part 2, after we have done so we talked about the analysis first, then we talked about the simulation. Now we come to the measurement, right? So before we go to the measurement, do you have any questions on the simulation and how you record the simulation results?
No, it was actually pretty clear.
Okay, great. So again, whatever you cannot record, you can calculate. So what about the analysis? Let's talk about the analysis for a minute, right? So again, like I said, you are going to follow the example for your analysis. So let's go back to our sample lab report. So this is our sample lab report here. We have our table showing the results. We have simulation results. I'm going to go ahead and put some analysis results. Table 1, I call it series. analysis results. Now, if you remember, I did give you guys a document. I sent a announcement, right? And in the announcement, I put a sample document. I think I still have it here. Let's have a look at it. So in the announcement, I put the sample document. So let me just pull up that document and see how easy it is to go ahead and do analysis for. How easy it is to do analysis for. So here's the document. So in this document, you can see we have examples for Ohm's law, right? Following this, we have examples for a series circuit, yeah? Then we have examples for parallel circuits as well. So it's very easy for you to simply, and I ask you to complete these examples. So I'm going to copy the results for a series circuit. In my lab. So this is my series circuit analysis. And then I'm going to do the same thing for the parallel circuit. So this example already has most of the equations that you're going to use, right, for your analysis. So I call this one parallel. Parallel analysis results. So I'll go back to my example and I'll copy, because it has most of the equations that we use for parallel. So if you notice here, the first one, I only did one of them, but you can see that we can very easily do the, I asked you to solve this one, right, with 3 resistors. And I already gave you an example as well. So again, I'll just copy this. And of course, it has to be modified. It has to be, all the values have to be substituted so that I can know that this is correct for the particular circuit that we are working with, right? For example, we don't know what is given here. R1 is not 900, right? So you need to say what R1 is. So for example, here we can say R1 is equal to 100, R2 is equal to 220, R3 is equal to 1K, DS is equal to 5 volts. So this is the known values. This is what you know for your circuits, right? So using that, you can go and solve the problem here, right? Now, there are other ways you can do the analysis. So you can do it like this by hand, where you go and calculate everything, yeah? Or you can actually program these equations into Excel. And so if you program the equations into Excel, then you can actually solve it using Excel. So that is one way you can do it, and you can do it very quickly. And so I can give you an example. So let's give you an example. So I'm going to do it very quickly, so you have to follow me quickly. I'll copy these guys right here, and I'll open up Excel. Let's go with new. So if you, again, the most important thing is to know the equations. If you know the equations, then you, let's call this R1. If you know the equations, then you know which one to use. Then you can calculate it by hand, but you can also program it in Excel. Excel is a tool that is free to use. I'll just put R4 in case we have 4 resistors, right? And then I'll say, okay, so the value for R1 will go here. So let's go ahead and put 100, and we'll put 220, we'll put, let me make it bigger so that you can follow. Because you need to see the equation line at the top as well. This is 1K, so I'm gonna put 1,000. So everything here is in ohms. So I can see here, this is, let us just put the borders on. And I'm gonna center it. Very good. So R4, we don't have an R4, I'm gonna put 0, right? Okay. So the first thing we want to know, let me just put this somewhere else. Let's put it there. The first thing we want to know, right? After we know R1, R2, R3, what is RT? RT, right? So here you put the equation for RT. What is RT? RT is the sum of all the resistors, correct? So it's going to be equal to what? You can just say sum of the resistors. Make sense? So we calculate our RT here. And now this is in ohms, right?
Right.
So we can say, okay, in ohms, so that someone does not get any idea that it is in kilo ohms or something like that. So we can just say this is RT in ohms. Okay, I don't know why the brackets don't want to behave. Okay, let me just fix it to square bracket instead. All right, so RT in ohms. The next thing we can calculate is, okay, so we given R, what about VS? We need to have VS as well. So we can say that VS is equal to 5 volts. So I'm going to add it to the table. That's what we are given. So what is IT? IT is going to be equal to what? According to Ohm's law, IT is V over R. So it's going to be VS. So instead of typing VS, we just go and click VS, or we say equals. We click here 5 volts. Now, of course, it doesn't have to be 5V, it just have to be 5. 5, and then we say divided by what? RT, whatever is here. In our case, it's going to be 5 divided by F7, right? So again, this should be just 5. So this is our IT. And again, notice it's in amps, right? If we wanted to convert it from amps to milliamps, we have to actually multiply by 1,000. And then it's going to be in milliamps. So in the equation here, let's go ahead and just do multiply by 1,000. And that can help it here, so we can know that, okay, and we can say here that it is in milliamps. The next thing we want to find what is the total power, PT. Now, of course, here we can say that PT is going to be equal to V squared over R, so we can say it's equal to V squared, so V times V divided by RT. So this is our power in watts. Now we can also convert it into milliwatts if we want as well. So I'll just put it in milliwatts. And again, the way we convert to milliwatts, we need to multiply by 1,000.
So we have to convert each answer to milliamps to milliwatts?
No, we don't have to, but sometimes you'll be asked to do it. So again, here, how do you calculate the voltage across V1? And like we said, there are different ways to do that. We have the voltage divider method. We have the Ohm's law method. Ohm's law method says multiply I by R1. And so that's easy to do, right? So we can say VR1, VR2, okay, hold on. VR1 here, VR2, VR3, VR4. We don't have any VR4, okay? So how can we do that? A good way, easy to do it, just Ohm's law times the resistance. So we can say that that's going to be equal to, V is equal to I times R. What is our I? I times R. R. What is V? This one here is equal to I times R. Now this one we can find in the voltage divider method is going to be equal to R3. Okay, hold on. It's equal to R3 divided by RT times VS. That's the voltage divider method that we talked about. So you can use that. It's actually more accurate than the Ohm's law method. What's the next thing you're asked to find? The power rating for 1 and 2. So we can actually find the power, and then we can find the power rating afterwards. So power 1, PR2, power 2, PR2. Again, so what is the power for the resistor? It's going to be V, the voltage across the resistor squared, V times I, right? The current flowing through the resistor times the voltage of the resistor. That's one way you can do it, or you can use V squared divided by R, where V is the voltage across the resistor. So we can see that P is equal to VR1 times, so we'll use that one, VR1, divided by R1. And the power rating, now this is in milli. So again, because the power is in milliwatts, okay, hold on. Okay, I think our voltage is in millivolts. So let me just change this back to, anytime we have the, I'm gonna change this back to watts. So you see, if we convert our current to milliamps and we use it, then it will affect our readings. Our readings will be in milliwatts already. All right, there we go. So if it's not in milliamps, then we move the 1,000. And for the power, of course, we move the 1,000 as well. So notice here, our power is going to be V squared over R. And the power rating is going to be this one times 1.2, right? Is the power times 1.2. Same thing for this guy here. We can say this is equal to VR2 squared times VR2 divided by R2. And of course, PR2 is going to be this guy times 1.2. So you see, it's very easy to, the same equations you have, you can program them in Excel. So if you wanted to change the circuit around, you only change this variable here and everything else is calculated for you automatically. That's, if you do a program like that, you can definitely reuse it to solve some other problems. And this just shows you some of what, so when you go to simulate the circuit, the computer is using some of the same equations to give you the answers that you're looking for. So again, if you look at the lab handout, the sample lab report that I'm showing you, you can simply solve your problem here. Okay, hold on, it's the wrong one. Close this. You can simply solve your problem. So this is your lab. Notice here we have the analysis, parallel analysis, and then we have series analysis, right? So you put your answers here. Now, whatever answers you get, these answers, you put them in the table, right? So for example, let me see if I have some answers for the table right now. If I go to my Excel sheet here, I can see, okay, I have all of this here. Let's copy this. So if I go to my table, I can put this stuff in because I have it right here. I have the series data for sure. So RT, I can put my RT in. All of this will come under analysis results, right? RT, I have the total current, I have VR1, VR2, PT, all of these I can put in from my analysis. If you complete the table here, you're going to have pretty much the same results in your analysis, and you'll be able to copy it in the table. So your table should be complete. You need to know how to do analysis. This is one of the objectives of the lab. You need to know how to simulate, how to use the simulation tool to obtain your results. This is another objective of the lab. And the last objective, you need to know how to obtain the measurement results. You need to know how to measure, use the digital multimeter to do those measurements. You need to know how to use the breadboard to connect the circuit and so forth. So this is what we're going to do now very briefly. So the last step in the procedure is about the measurement. So I'll take this here. So for measurement, it tells you to construct the circuit, measure the resistances, and also then take some pictures and record your data in the graph. Then it tells you what to measure. Measure total current in I. So for the series circuit, it tells you to measure VR1, VR2, and VR3. Then it tells you calculate the power. It doesn't even tell you to measure the current, but of course we can measure the current. For the parallel circuit, it tells you to measure the total power resistance. It tells you to measure then the total current in I1, current in I2, current in I3, and then it tells you to calculate the power. So this is what we're going to do here. So I'm going to share my screen with you. We're going to do it again very quickly. Again, the steps: total, series, resistance, then the total voltage drops, and then the current. So, and of course, we're going to put our results in the table right here. So we already started. So I'm going to remove this. All right, so at this time, we're going to be doing the lab experiment. These are the parts that you need. You need 2 jumpers here. You also need 3 resistors. And in these resistors, we have one 1K, we have one 220 ohms, and we have one 100 ohm resistor. And again, this is the circuit that we are following. I'll just do a quick scribble. Remember, we have a 5 volt source. We have our 1K ohm resistor, so 100 ohm resistor here, 220 here, and 1K here. And again, for the meter, the black in common, the red in V ohm, and I'm going to put it on the omega symbol. So I know that the highest resistor I have is 1K, so I can put my resistance down to at least 200 ohms to measure the other values. So if this is the 100 ohm, then I can put my resistance down even further. So if you notice this, my meter is on 2000 and this is reading 999. So this is my 1K ohm resistor or 1000 ohms. So the resistance is going to be 100, or it's going to be let's go with 1001 ohms. So I can say that R3 is equal to 1001 ohms. So this is my R3 here, right? Then I go to the next resistor. And this is my 100 ohm resistor. So my meter has another setting for 200. So I can use that one so it can be more sensitive. And so the resistance is 100.3 ohms. So this is going to be my R1, 100.3 ohms. And then, so again, I put it right here. This is R1. And of course, the next one is going to be R. So again, this one, the maximum is 220. So I'm going to put it on 2000 here. And it gives me my resistance, 224 ohms. So R2 is 224 ohms. Now, this is the first thing you need to do in your lab in terms of your measurement, and you're going to record this in your table. What am I talking about? If you go to where you're doing your lab report, in your table, you need to record this measured data. So if you look here, the first thing you do, you take that data that you measured and you're going to put it in your table, right? All right, let's continue. So first, we're going to start with the series circuit, right? We need to connect the circuit as it is in the diagram. So for our power source, we're using a battery. We have a battery symbol right there. But instead of the battery, we're going to be using the Arduino, right? So if you notice here, instead of the battery, we're using the Arduino. So this is our breadboard right here. This is our Arduino here. And on the Arduino, we're going to use the 2 pins, the ground and the 5V. See here, ground and 5V. So ground is going to be used for our negative of the battery. And so I have a black jumper in here. And 5V is used for the positive of the battery. So I have the positive here for 5V, right? And so again, this represents my battery. This represents the positive, 5V, and the negative is GND on here, right? So I'm going to put this down here. The first thing you need to do, how do you use the breadboard? Again, the breadboard, we said if you want to connect 2 things, we just put them in the same row here. So I'm going to go ahead and put my jumper from my 5 volts from my battery in the breadboard. According to my schematic diagram, I need to connect the battery, which is this here, to a 100 ohm resistor, which is my R1. And I believe this is it right here. Just verify. So I need to connect my 5V to this resistor. And so what do? I simply put them in the same row and then they are going to be connected. So if you look here, I just need to put it in the same row here. Any one of these here is going to be fine. So I'm going to put it in the same row and I'm going to go across here. All right, so I've just completed this. Yes. Now I need to connect the 220 ohm resistor to the 100 ohm. So I take this resistor, one leg of it is connected to the 100 ohm, the other leg should be connected to the 1K. So I'm going to put it in the same row here so it can be connected to the 100 ohm. So again, it doesn't matter if I put it next to it or the one up, as long as it's in the same row. Okay, and the last step is to connect my 1K ohm resistor. So I'm going to just put it here. Thank you for joining us, Mr. Bryce. Okay, so the last step now is for me to use a jumper to connect the negative of the battery. So I have done this here. We have connected this. We have connected this. We have connected this. The last step is to connect the negative of the battery to the other leg of the 1K ohm resistor. And we said that we are using the GND on the Arduino for that, right? So I'm going to put a jumper in the GND and I'm going to connect it in the same row with this pin here. That's how I connect things. Just put them in the same row. And now the circuit is complete. It's connected, right? So now I'm going to power up the Arduino. I have a battery bank right here, the USB source. So I'll just put it in the USB so we can have some power. Okay, the light just came on, so it means we have voltage here. So now we are ready to do our measurements. So what are we going to measure? We're going to measure VR1, VR2. We're going to measure VR3. Then we're going to measure the total current, right? That is coming in. We can even measure the VS. According to KVL tells us that our VS is going to be equal to VR1 plus VR2 plus VR3. So in other words, Kirchhoff voltage law says that all the voltage drops is going to be equal to whatever voltage we have coming in, which we know is about 5 volts. So let's go ahead and start this measurement. So again, on your meter here, if you go on voltage side here, what we see here, we have 20, right? The next one down is 200 milli. Now, of course, we are measuring some measurements we have are below 2 volts, so we can use this. But for most of that, for 5 volts, we need to go on to 20. So let's start with 20 first. So again, meter is right here. Again, the meter is still the same configuration, V ohms and com. And we are measuring. So how do you measure voltage? Again, just put the pins across the terminals. So again, if you want your voltage to come out positive, you need to put your positive pin on the side where the positive voltage is entering the circuit. So again, if you look here, we see that our positive is coming in right here. So again, you just need to touch the pins. An easy way to do that is to put your pin in put the leads of the meter in the same hole as the leg of the resistor. So again, if you put your pin in the same hole as the leg of the resistor, you're going to make contact with the pins, right? So if you notice here, the voltage is 0.037 volts. So this is lower than 2 volts. So I can move to the next range down. So I'm going to measure again. So my results are going to be more accurate. Now my results are coming in millivolts. So the answer, the measurement is 366 millivolts, which is the same as 0.366 volts. So I can record that. This is going to be 0.366 volts. Then I move to the next one. Okay. Again, we said that for the series circuit, the smaller resistor has a smaller voltage across it. So that's expected. In this case here, putting the pins in the same hole with the resistor. So if you look at the leg here, I'm going to put the pin in the same hole so we can make contact with it. And so the meter is showing me 803 millivolts, which is the same as 0.803 volts. Actually, 0.804 volts. So this is 0.804 volts. And then for the third one, I'm going to change the range because I know it's going to be over 2 volts. So again, I put it in the same hole here with the pin. And notice the measured voltage is 3.67 volts. So I'm going to make a note of that. 3.67 volts. Like I said, if you add this, they should be very close to 5 volts. So I use the calculator here. So we have 0.366 plus 0.804 plus 3.67. So again, very close to 5 volts. Let's measure them again. Again, we have 3.67 plus 0.804 plus 0.366. Very close to 5 volts. Then we can also measure the voltage coming in. So let's go ahead and measure the total voltage coming in. Now your measurements may be a little different than mine because although we have the same components, like we said, because of the manufacturing tolerances, your values will be different than mine. So again, the total voltage coming in here is I guess my battery is running down on my, it's 4.85 volts. Again, 4.85 volts is the total voltage I have coming in. So the last step is to measure the current, right? Now, just before we measure the current, I have another meter here. So I'm just going to double check my measurements with this meter. See here so that you don't see a glare. All right, so this is better, no glare here. So my meter is on voltage and I want to measure the voltage coming in. I just measure it again. And it's 4.94. So the other meters, it has some error. So how do we measure current? So again, to measure current, very important. We need to configure the meter to measure current. What is that? We need to move this red lead to the current port, either ampere or milliamp. So I'm going to move it to the milliamp port. Then we need to turn the dial to the milliamp selection here, so we can measure current here. Okay. Now for you, based on the amount of current you're measuring, you will adjust the meter that you have. Next, we need to, after we configure the meter, we need to disconnect the circuit and then use the meter as a jumper. So again, I'm going to disconnect the circuit here. And I'm going to use the meter as a jumper. So what does that mean? This is going to jump between the two of them here, and I should see the amount of current that's flowing the circuit on the screen. So again, I put my positive pin here, my negative pin here, and notice that the total current that is flowing is, see here, make sure we have some firm connection, 3.76 milliamps. So the total measured current, I, is it's going to be 3.76 milliamps, right? Again, the meter shows me milliamps, so I know exactly what I'm doing. So this is all you need to do for the measurement part. You can use these values to, of course, calculate power and so forth. We know that power is equal to V times I. So we can say, what's the power in R1? It's going to be VR1 times I. And again, if you wanted the power rating for R1, PR1 is going to be P times 1.2. Okay, so let us now look and see what we do for the parallel circuit. But just before we do that, what about your meter? How will you measure current if your meter? Again, you need to go on the current side for DC, and you need to go maybe start with the maybe 20 milliamps, and you can go to the lower setting. This one is for 200 milliamps. This is like 0.2 milliamps. So this is the lowest, okay. This is the lowest setting, 2 microamps. So you can go start with like the 20 milliamps. And if you need something lower, you can go here. This is the highest range for this is 2000 microamps. And this is the same as 2 milliamps. So you probably want to start right here. So let's do the parallel circuit, and we'll see, of course, this circuit will draw more current, right? Okay. So we'll start by drawing just a simple parallel circuit. So again, we have R1 here, which is 100, R2, which is 220, R3, which is 1 k ohm. And we have our VS, which is 5 volts, right? Okay, in this case here, we have our resistors, same resistors we had here. I'm just gonna put them down here so you can see them. Okay, so this is our resistors right here. All right, let's see. This is our resistors here, and I need to build a circuit on the breadboard. So again, if you notice the circuit here, to connect the resistors, both ends of the resistor have to be connected. So this end must be connected to this end, right? So in other words, it's almost like this. This is what the parallel circuit looks like. All the ends of the resistor are connected. So how do we do that on the breadboard? Okay, so we'll start with R1 here. So just take your R1 and put it in the breadboard like this, yeah? Now we said to connect something to this, we just have to put it in the row here. For some reason, I'm super dark. Let's try to make it better. Okay, so again, to connect anything to this resistor, we need to put it in the row here. So of course, I'm going to take R2 and put R2 in the same row as well. So now both ends of R1 and R2 are connected because everything we put in the same row is connected. So they are connected now, they are connected now, right? And of course, we have R3, put it in the same row as well. So it's now connected as well. Now you can see that we take our battery and we put our battery in the same row. Now I'll put our positive in this first row here, and I'll put our negative in the second row here. So if I put the positive here, so if I turn the circuit, you see it looks just like our diagram, right? All of these are connected because there's a connection at the bottom here. So let me put the positive here, and we'll put the negative there, right? So this is our parallel circuit. Now, of course, we said whatever voltage comes in here is across all of the resistors there, yeah? How do you know that? I'll put my meter to measure voltage. In fact, let's go back to your meter here. No problem, I'll stick with this green one. So again here, we have a meter measuring voltage here. So if you measure across this here, you should get about 5 volts. So we are still in the milliamp. So I need to turn my meter. So again, to turn it, I need to put it to measure voltage here. And also I need to move the port and put it back in V ohms to make sure I'm measuring voltage, or else I can damage the meter. Okay, just give me a second as I plug my computer. Make sure we don't run out of power. All right, great. So we're going to measure the voltage coming in here, and of course, it's going to be about 5 volts. So if you look at the screen of the meter, you will see that the voltage is the same for all the components. It's about 5 volts for this one, and for that one as well. For that one, the voltage is about the same. Notice that our voltage went down. That's because the amount of current that we are drawing is increased. And so we'll talk about that in the class. We'll talk about the ideal voltage source and a non-ideal voltage source. So you'll see as we draw more current, our voltage has actually decreased because our voltage source is not ideal. So you see it's about 4.5 now because we are drawing more current. Okay, so now off to the measurements. With our measurements, we are measuring current, right? We want to measure the current that's coming from the total current coming from the battery, right? So A represents the ammeter. We want to measure the current in this branch as well. So the current that each resistor is drawing, that's what we want to measure, right? So again, to do that, we need to put our meter to measure current. So we can simply turn it over here for milliamps, and then it needs to go in the milliamp port. And then we need to disconnect the circuit and use the meter as a jumper. So the first thing we're going to do, we're going to disconnect the main voltage coming in, right? And then use the meter as a jumper so that we can measure the total current being used by the circuit. So what is IT? Okay, IT. What is I1, I2, and I3? So again, from the simulation, I believe it was about 70 point something milliamps. So here. Now keep in mind that our voltage has reduced. So we have to take that into consideration when we actually measure the current. If you're using a power source like your USB from your computer, it's going to be the same, but my battery is going down. So total current is showing me 64.1 milliamps. So I can write here 64.1 milliamps. I will also write the VS, we said about 4.5. Then I need to measure the current flowing in R1. So essentially, I'm measuring the current in R1 by itself. So I need to disconnect. Okay. I also think I forgot to measure the resistance, so I'll do that as well. So I want to get the resistance for R1 by itself. So this is R1. So I disconnect it from the others. And now I'm going to see what is the current flowing through R1 alone. Okay, so the current for R1 alone is 4.97 milliamps. Okay, and I want to apologize. This is not R1, but this is going to be R3. So this is I3. The current for I3 is 4.97 milliamps. So this is 4.97 milliamps. So then I need to get the resistor, the second resistor by itself. So I remove this one. So again, they are no longer in parallel. Only the bottom side is connected, but these are not connected. I just want to know, okay, what is the current flowing through this resistor alone? Yeah. So I'm only making it so it's only part of the circuit. So in essence, the circuit we have is just the same as a battery and one resistor. And I'm just measuring the current that is flowing. That's how we are doing it, right? So again, I put my lead on this positive pin and on this resistor. So this is our R2. See, the current is 21.9. Okay, let's make sure we have some good contact. 21.96 milliamps. So I2, 21.96 milliamps. And the last one, which is our I1, you will see we'll have the most current. So I1 has 44.3 milliamps. So the smallest resistor will draw the most current, 44.5 milliamps. All right, and like we said, the current flowing, the total current is based on the sum of the individual currents. So if we decided to measure the current here, it's going to be the current here and here. And so we can do that if we have our 2 and 3, and we, so if we have 2 and 3 together, and we measure the current, it's going to be equal to the current of these two. So let's do that. I put them back in parallel here, so they're in the same row. And now I'm measuring the current. And again, it's going to be 26 point, let's make sure we have some good contact. 26.23 milliamps. So call this I23. Let's call it I23. I23. 26.27 milliamps. Again, you see it's going to be this one plus this one, right? So again, the total resistance is, if we add I1, I2, and I3, we're going to get about 64 milliamps. And this is what the lab wanted you to see, right? That you obtain the same results from analysis, simulation, and measurement. But of course, the techniques, how to use the breadboard, how to connect a circuit given the schematic diagram, how to use the meter to do the measurements, right? Any questions before we stop? So again, you take these results and you put them in your table. So if I show you my screen, this is the sample report that I was doing. You put them inside of here, right? Also keep in mind that you are asked to take some pictures as well, right? So for your measured results, you need to take some pictures. One thing I forgot to do was to measure the total series resistance and the total parallel resistance. So I'll do that now. So we don't need any power to measure resistance. So we simply put the components in parallel and we measure the resistance. So the total parallel resistance is 64.8 ohms. So our RT, 64.8 ohms. Now, of course, if you put them in series, we said the resistance is going to add up. So it's going to be 1K, which is 1,000, plus 220, plus 100. Do you have a question for us, Bryce?
Well, not about this, but I mean, I do have a question.
Sure, go ahead.
So you know how you said I had talked to you before I left, right? About the school.
Yep.
And I was just making sure that I still be able to make it all up whenever I come back.
Yep.
Okay,
yeah, so we said that everything, you need to submit it before the 20th of June.
Okay, yeah, I come back next Tuesday.
Yeah, so as long as you turn it in, that's it.